Alright, think we'll get started. It's just a small demo about things that you have already studied, right. So, this is a transmission line, alright. In specific, it is a kind of a transmission line, alright. So, this particular one is a coaxial cable, alright, and there are many kinds of coaxial cable that you can find in the market. This is just one version of them, right. So, it has a connector at the center and a connector around it, I mean a conductor in the center and a conductor around it. So, it is a straight conductor in the center and then a braided conductor around it, and the ends are having some kind of a connector. These are SMA connectors, sub miniaturized version A SMA connectors that can go into some devices which can probe RF. Okay. So, here we are having a specific cable, alright. So, I believe this is RG136. Okay. So, it is radio guide 130. There are number of coaxial cables that you can buy depending on the application. This particular one goes up to some 500 megahertz to maybe 600 700 megahertz with reasonable losses. Okay. So, this is a typical transmission line. Okay. There are also other things that we have. So, I have an different cable over here. It's an RG58 cable. So, this is a 50 ohm characteristic impedance cable. This is also a 50 ohm characteristic impedance cable. They come in different lengths, alright, different colors, different composition. For example, the center could be made up of copper, or it could be made up of copper coated steel, or it could be braided with aluminum on the top. The jacket material could be different in different companies. So, it just depends, alright. So, these are also very rigid. You cannot bend them with very short radii. There are guidelines for how much you can bend them and how much you cannot bend them and all that. Okay. So, these are some short stubs of cables that I thought I will come and show you, but most of you may have set top box in your houses. You must have seen a coaxial cable in your houses. That particular one is known as an RG6 cable, okay, radio guide 6, and the good thing about that cable is it's fat, so it's less lossy, alright, and it goes up to 3 gigahertz. Okay, up to 3 gigahertz. So, that is much better cable than what we have here. These are short stubs, alright. So, what I will do is, there are more patch cords over here, alright. This particular connector is known as an SMA connector, alright, and this is what you will commonly notice in microwave labs, etc. Okay. Now, what I will do is, I will show you some specifications of these cables first, then I will show you where these cables are connected, alright, and then I will show you the specification of the machine to which it is connected, alright, how to read a data sheet and all that, and then we will see how it solidifies what we have learnt in the class. Okay. So, I will first start with cables. Okay. I am opening for some common cables. RG58 is a very common cable that I learnt to use maybe when I was beginning to read this. Okay. So, let us have a look at typical specifications of your. So, if you look over here, impedance Z0, this is the characteristic impedance of the cable, alright. So, there are different varieties RG58, 58A, 58B, 58C, etc. So, all of them have a nominal impedance of about 50 ohms, so 53.5, 52, 53.5, 50 ohms, etc. These are some nominal impedances. So, the dielectric material in all of them is solid polyethylene is what is given, alright. So, this is the material between the center and the outer braided. I will show you how the structure looks. I cannot cut this cable, but I will show you how the picture of what it would look like. Time delay nanoseconds per feet using some combination of SI and imperial units, does not matter. If the manufacturer is from English countries, then you will have nanoseconds per feet, alright. So, also in US it is pretty common to use feet, etc., but does not matter. Alright. So, time delay is 1.5 nanoseconds per feet, and then they give you something known as propagation velocity below that, percentage of C. Here it says that it is almost 66%. Okay. So, typical cables have velocities of up to 2 times 10 to the power 8 meters per second. This is the velocity. Okay. So, the first class we said that no signal will travel at infinite velocities. The upper limit is the speed of light 3 times 10 to the power 8 meters per second, and in most of these cables which operate at say gigahertz frequencies, the propagation velocity is 66% the speed of light. Seems to be very common, right? Maybe you can pick up varieties of cables, 66% the speed of light is about 2 times 10 to the power 8 meters per second. Okay. Now, there are also other things which will solidify what we have seen in the class. For example, capacitance is measured in picofarads per foot. We said that it is a distributed parameters in the first few lectures, alright. It is given as 28.8 picofarads per foot. Now, I think it should be clear to you that this is how the specifications are given. It is a distributed parameter. So, the longer you buy, the more the capacitance you will be adding per foot. Right. So, some outside dimensions, and we also did dB calculations for input output powers, relative power, etc. So, it tells you how much of loss you are going to be having in your transmission line. Here it says that it is about 11.7 dB per foot, but we have to take all these things with a pinch of salt. This may be the best loss or this may be the worst loss. It cannot be the worst loss because it is only 11 dB. So, maybe it is somewhere in between. Okay, we will see more details later. Okay, and it says maximum, okay, so it tells the dB per foot it has 400 megahertz. Okay, at 400 megahertz about 11.7 dB decibels per foot. You can always go back, use our formula and try to calculate 10 log to the base 10 output power by input power is equal to minus 11 dB. How much is the ratio of V out to V in? You can make a calculation, alright, from the notes. Maximum voltage that you can apply is absurdly high, 1900 volts, okay, and the shield, that is the outer conductor that you are having, alright, and also to provide it insulation from external electric field. So, this outer braided conductor is, it is a braided conductor, it is not a film or something like that. That is the detail that is given, and then there is some tidbits of information. If you see here, the RG58 cable is most often used for thin internet, alright, when the maximum length is about 185 meters. Now, this is a piece of information that you may not have been aware of. Okay. So, it is used for thin internet, okay, when the maximum length required is about 185 meters, of course, right. Nowadays, we have Wi-Fi, cell phones and all that, but if you want to have a wired internet connection, this could have been not this particular RG58 would have been a candidate, this is a different one, I think it is 319 or something, alright. So, you could also have different connectors at the end, you could have a BNC connector for low frequencies, you could have different types of connectors depending upon the application. Okay. So, this is how the cross section looks. Because I could not cut these wires, I just wanted to show you that there is an outer part, alright, and then there is a braided conductor inside, and there are different cables, we saw RG58, AB, etc. Some of the specifications could be slightly different because of the materials and the way they are being used. For example, I can see clearly that the outer braided part is copper in the first one, alright, and it is aluminum or maybe steel, I do not know, alright, looks like aluminum. And then there is a dielectric which is polyethylene in this case, and then there is a core which is again copper. This is what is the structure. So, the central part of the wire is connected to the pin over here which is going to carry a signal, and the outer one is going to behave like a ground. Okay. So, these connectors are just pressed and crimped, that is it. Okay. So, the outer part has to make contact with the outer copper thing that is present over here, and the center part has to make contact with the center male part over here, that is all. Okay. So, again this is a 50 ohm connector, 50 ohm cable, right. So, there are many more things that one can read, right. So, I wanted to just put this also. This is a very good document because it also gives you some limitations about what can be done, what cannot be done. RG58 cabling supports up to 30 nodes, maximum distance of 185 meters. Okay. So, I think this is very interesting. Let us look at some more things related to the cables. So, this is another company which makes cables, RG58 according to the standards. Okay. So, it is 52 ohms nominal characteristic impedance, all right. So, it also tells you what is the gauge of the solid core that they are using, what is the diameter of the copper conductor in between, I mean in the center. Okay. So, it is saying that 0.033 inches 20 AWG is the gauge of the solid core that is present over there. Polyethylene insulation, now we can understand that there are many commonalities across manufacturers because they are conforming to some kind of a standard. Right. So, bare copper braid shield, then they say there is a PVC jacket on the outside to protect that. Right. This is the composition, right. And I will just go to some technical specifications. So, again solid core, polyethylene dielectric between the two conductors, okay, braided outer shield, right, PVC outer jacket material, and then let us see something nominal conductor DCR, right. So, this is 10 ohms per 1000 feet. Again you notice that everything is coming in distributed units, okay. 10 ohms per 1000 feet, this is the typical resistance per unit length that you will be having in these cables, right. 10 ohms per 1000 feet, or for the outer shield is 5.5 ohms per 1000 feet, right. So, it is a very tiny amount of resistance depending upon the application. You cannot use it for very, very long connections anyway. So, again capacitance, nominal capacitance conductor to shield, that is conductor to shield measured across the two conductors with a dielectric in between, is again distributed parameter, which is 28.5 picofarads per feet. So, everything is in distributed parameters, and nominal inductance is 0.08 microhenry per feet. So, these are roughly the range of values you can expect, some 100 picofarad capacitance per feet per foot, all right, and orders of microhenry per foot, right. This at least that much you should be knowing. You cannot absurdly write Henry, Farad, etc. So, these are very tiny values of capacitances and tiny values of inductances. This is just for you to get a feeling for the numbers in actual cables. Nominal characteristic impedance is 52 ohms, and then high frequency insertion loss, that is output power to input power, right, taken in dB. Also you see how it has been given at 1 megahertz it is only 0.3 dB per 100 foot. Not sure, are you able to see? Right. It is only 0.3 dB per 100 foot, 10 megahertz 1.1 dB per 100 feet, and then at 1 gigahertz it is 14.5 dB per 100 feet. So, the lesson here is, as you start having higher frequencies going through these cables, the losses will typically become higher. Okay. So, this also means that a transmission line which worked for low frequencies need not necessarily work for very high frequencies. Okay. So, the general rule is, as your frequency increases, the loss increases. That is the general rule that we are seeing over here, right. Again, the delay is 1.5 nanoseconds per foot, that means that it is about 66% of the speed of light, that is 2 times 10 to the power 8 meters per second. The voltage that you can give is about 1400 volts, so similar to what we saw with the other manufacturers, 1900 volts, etc. On top of that, they give you an operating range between minus 40 and plus 80 degrees centigrade, and then on top of that there are some mechanical characteristics, how much you can pull, how much you can bend, all these things could be provided. So, these are typical data sheets of cables that are available in the market, okay. And there are some variants, right, and different variants may have different color jackets to just tell them that yellow color is for this, blue color is for this, black color, it could be like that, okay. So, I think by now you should be able to at least digest the fact that many of the transmission lines available in the market for high frequencies indeed indicate distributed parameters. Seems like a very common termination impedance or characteristic impedance is about 50 ohms. The ones that you are using for your cable TV RG6 cables have characteristic impedance of 75 ohms, they are not 50 ohms, okay. So, it depends, but 50 and 75 ohms are reasonably common, okay. So, I think there are many more with respect to the cables. If you have time, you can always Google. There are many companies which provide the same information in different ways. In this case, this is another manufacturer which is giving you properties. It says that characteristic impedance is 50 plus or minus 3 ohms measured at 20 degrees centigrade. Capacitance of the order of 100 picofarads per meter. I just picked this because it had units in SI. So, resistance for the inner conductor is about 36.5 ohms per kilometer. All right. So, velocity ratio 66%. At this stage, you should at least know what numbers to expect from your transmission line. Okay, and things that are available to you when you are buying a transmission line is these data. People give you the velocity factor. People give you the impedance per unit, characteristic impedance and capacitance, inductance per unit length, etc. Okay. So, I think this is the basics of a cable. Now, what we are going to do is we are going to use these cables. I just picked this up from a lab, but the lab has very sophisticated instruments. Okay. And one of the instruments that the labs in IIT have is vector network analyzer. In short, they are known as VNA, okay, vector network analyzer. These are the equipments that are made. So, I will open one of them as to how it looks. Some people may have seen this and thought that these look like giant oscilloscopes. That's close to what one can guess. So, I think in the RF lab in IIT Madras, they have a couple of these, right. So, this is from Keysight and this is how it looks. It is actually a giant machine, all right, and it costs about 60 lakhs, all right. So, that is why I could not carry it here and show it, because on the way if I dropped it, that is it, I have to repay for it for the rest of my life, and my child would have to also pay it. Right. So, this is how it looks. It has some inputs. You can see that they have some specific connection types. Okay. So, these could be depending on the frequencies or depending upon the availability, etc. But there are also adapters to go from one type to another type, etc. There are adapters which will allow you to do that. So, if you see the screen, there are some plots. Typically, they analyze in these cases S parameters. Okay. So, we have not seen about S parameters, and we are not going to see about S parameters in this course. In an advanced course in waveguides and antennas, you will be dealing exclusively with S parameters. They measure the S parameters, specifically S11 and S21. Okay. This is what is being shown here with respect to frequency. On the right hand side is something that should be familiar to you, which is a Smith's chart. Okay. So, you see that there is some display here with the Smith's chart. So, the hardware nowadays comes with this ability to plot impedances on a Smith chart. So, you would connect a cable to this, then you would have a device, all right, and then maybe you have some termination. So, you see on the Smith chart what is the impedance that is seen, all right. So, it can be used for a variety of purposes, but these are things with very high capabilities. Okay. They can go up to maybe 18-20 gigahertz. Okay. Whereas the cable that we have is no good for more than even a gigahertz. So, you need to use specialized cables for them, and these are wonderful equipments, temperature stabilized, etc. This is another equipment from Anritsu, which is also a company which just looks like this. I just wanted to give you a feeling for across manufacturers. It also has multiple ports, all right, port 1, port 2, all right. It also has different connectors, and it has Smith chart based plots, etc. Okay. So, you could connect in theory a transmission line, you could connect some impedances, you could connect say filters, you could connect different things that you want to make for these frequencies and analyze what is going on with these equipments. Okay. This is also probably equally expensive. Nowadays, we are getting something of slightly lower specs, but something which I think really suits studies in universities, which are these mini vector network analyzers. So, this is a mini vector network analyzer. Okay. So, all it does is it takes in some input, it has a transmitter which sends out, which is your source in our transmission line course, and it has a port for receiving the data. So, it has a receiver, and then it has some processing, and then it connects to your computer, and it has its own dedicated software to show us what is going on. So, this is all it is. All this big equipment that you saw have extraordinary abilities, but this is good enough for most of the day to day work, for at least for studies and for amateur radio enthusiasts, etc. This is a very, very good piece of equipment. To give you the cost comparison, I gave you the cost of that to be about 60 lakhs in Indian currency. All right, this is about 500 to 600 US dollars. Okay. It's about 30,000 rupees. So, it's an order of 100 lower than the cost of the big machines. So, I think for universities which are looking at having curriculum for just doing some demo, etc., they can always purchase one or two of these and have some experiments going on. So, this is a mini vector network analyzer. All right. In particular, the one we have is made by SDR Kits. It's a company I think based in UK. All right. And so, this number that they have DG8 SAQ is the amateur radio sign for the inventor. All right. So, DG8 SAQ is person's ham radio code. So, he is behind the design of this. At the core, it has some ATmega microcontroller inside, and then it has some circuitry to sample, to up convert, etc. Right. So, this is what it is. Okay, I will quickly go to the part where it shows the circuit. We will not be able to make out much other than just understand that it is a simpler setup, but it's very, very handy and very useful. Gives you detailed instructions about things. Right. So, this is the board that is housed inside this box. I don't think we can read circuits just like that, but it's to just tell you that it is possible to make simpler versions of very complicated vector network analyzers that may have poorer specifications, but works just fine for most of the practical aspects. For us to understand many things about transmission line, these kinds of things are good enough. So, it has an upper frequency range of 1.3 gigahertz. That is good enough for us to look at most of the transmission line problems. So, this shows that it has a transmitter and a receiver, all right, SMA connectors, which are these parts over here, right. So, I think this is good enough, and there are now many more companies. There is a mini VNA at roughly at the same price. So, I think universities can procure this. Now, what we will do is we will try to use this, because I told that these are transmission lines. Let us just see how it operates and what you can expect, and whether we can confirm one or two things what we learned from the class using this, right. You want to do? So, this is the Smith chart screen of this equipment. All right, it's a mini VNA connected to the computer, and they have their own software to run this. All right, so it provides your Smith chart. This is something that we have generated on our own. All right, and all right. So, now I have nothing connected to this. So, I am going to remove these connectors. All right. So, it is an open circuit. All right. So, it is towards the edge. Now, you will notice that it is a little bit away, right. It is not right in this place. That's because every minute detail will start counting. All right. When you calibrate these devices, if you put something and you calibrate and say that this is open circuit, then that tiny detail matters. So, when we calibrated this, we had this on. Okay. All right. So, in practice, every single connector and every single thing that you do actually really matters. Otherwise, you will have slightly different results. Also, notice that we are running this for a single frequency, because in the class we have not seen multiple frequencies. Single frequency is all we have done. So, this is now your open circuit. Now, shall we connect a short circuit? So, So now we are having a plate which will short the inner and the outer conductors, right. And if you look carefully, there is a red color marker that is appearing on your screen, which moved to the extreme left of the Smith chart, indicating that it is a short circuit. Okay. So these are very simple things. Now I think you can connect a 50 ohm load. Remember that once again the connectors have changed, all right, and this is a 50 ohm load, and this TX RX output is rated for 50 ohms. Okay. So it should come at the middle, it's right at the middle, so it is impedance matched. Okay. So this is what, so these are some small things we can do. Since we are now seeing about the loads, we can always connect a transmission line. Okay. So we will connect a SMA cable with an SMA connector. I don't remember what cable this is. Okay. So it's open circuit, all right, but you notice that the mark is not exactly over here, because we know that depending on the length of the transmission line, you will traverse around the Smith chart. It will go all the way from a short circuit to open circuit. At lambda over 2 it will keep repeating, we know all that. So now we have a length of a transmission line that is giving you a position in the Smith chart over there. So we can estimate only the electrical length, we cannot estimate the actual length of the transmission line. Now just to make it abundantly clear, what we can do is we can also add another section of the transmission line to this. So he is adding a small section to it.
Total length.
Okay. So he is having a different length. Okay, it went to a different place. So now it should be clear that depending on the length of the transmission line, all right, you will be traveling, around in constant VSWR circles. Okay. So we are sweeping a constant VSWR circle. We could also go ahead and say that the load can be.
It is open now, we can short it.
No. Okay, you can short it, but shorting will again move in the constant VSWR circle.
Yes, yes.
But we can connect a load, because that's the.
Shall I put the load itself 50 ohm?
Yeah, because it will be impedance matched. It should come to the center, right?
Yes, yes. I want to know this.
If you need any connectors, use this. All right, great. Okay.
Almost.
Close. Okay. So impedance matching is not a joke, all right, and we are not doing it in the perfect ways either, all right. So we are having a 50 ohm load, and the frequency that we are doing is 100 megahertz. It says something else over here.
It's in the bottom. Yeah. 100 megahertz.
Ah, okay, 100 megahertz. So it's somewhere there, all right. Suppose I take this load and connect it directly.
You can remove that one.
You're better with this. Close to the center, all right. You have to believe if I say that it is impedance match, close to the R equal to 1 circle. Maybe we need to calibrate with the exact connector. So in practice, every minor detail will matter, but being the electrical engineer we are, let's deliberately do something, right. I have a couple of resistors, all right, that I have braided together. These are 200 ohm resistors. I think these are 200 ohm resistors.
Yes.
So in parallel I have connected them, so they should be 50 ohms, all right, and this is supposed to be 200 ohm resistors, so it should be connected in parallel and it should be 50 ohms. But 50 ohms at what frequency? Should be so usually when you buy 50 ohms for very low frequencies or DC. Okay. So now we are connecting this to say 100 megahertz. What is this?
It's in continuous mode.
Ah.
It's around here.
Yeah,
Almost 50.
almost there.
So it's continuously sampling here.
Yeah, I think it's okay. All right, but it's quite possible that at some other, you can see that it's actually in the lower part of your Smith chart, maybe some parasitic capacitance is there, so we never know what's going on.
One resistor.
Ah, one resistor. Okay. Problem is braiding is easy than unbraiding it.
Maybe one side is enough.
It will give very different because it will be open circuited in the other side. Okay, first of all, nobody will do experiments like this, but for the sake of class demo I'm doing, but I don't think this would qualify as a research thesis or anything, but it's somewhere else. But these are all the small things that you can do. Actually, it's a lot of fun having a mini VNA, and then you can do a lot of things. There was something we did with open circuit and short circuit, right?
Yes.
Okay.
It is reduced.
So currently, I think the transmission line is open circuited. All right. This was a question that was asked here. I want to determine the characteristic impedance of this. Open circuited ones. All right. And then you have to find out the impedance. So how do but you can notice that it's not on the horizontal axis. It's having a small amount of inductance. So I want to get the yeah. So it gives me an impedance of 234.45 milliohms plus J11.482 ohms. So this will be your short circuit impedance that you will see. So this is ZOC, right? And then we can connect the short circuit.
Open circuit is one.
Yeah, this is open.
Calculation.
Yeah, you could take these values and calculate a square root. It's okay, I think. It's fine, it's fine.
J11.
But the important thing is your characteristic impedance for open and short are supposed to have only like J, Z naught, tan, beta L. It's not supposed to have a real part at all. But in practice, you get a tiny real part, but the imaginary part is much larger than the real part. All right. So you will always end up with some tiny real part. Now it's a short circuit. All right. It moves to the diametrically opposite point, and if I wanted to measure the impedance, again, the imaginary part is much higher than the real part. Okay. So then you can use this for a number of other things. People using for antennas, waveguide studies exclusively use this VNA. I think now you have a feeling that what you are studying can be converted to some simple experiments, and you would be able to do them. So with that, I think we will stop. Next class we will jump to the next topic, which is going to be transmission and reception in the case where you don't have any wires.